In this section, we're going to talk about linear functions, which are basically functions whose graphs are straight lines. And so we have seen this before in an Algebra 1 context when we find the equation of lines. So whenever you've seen y equals mx plus b before, now we're going to recast that as a linear function that we'll write with our function notation this way. So we'll take everything that you've done before about y equals mx plus b, equations of lines, and talk about f of x equals mx plus b as a function, as a linear function. In the context of something like finding the cost of running a business, we have a linear equation that looks like this. So in this equation, the number here, that's like our y-intercept, is interpreted as, I'll put this in print, oops, that's not m, sorry, it's the wrong letter. So in the mx plus b form, that's the b. So when you think of the y equals mx plus b, that's the b part. We refer to this as fixed cost. So this is the cost when x is 0. So in other words, if you sell no coffee at all, then your coffee shop will still cost you $90 to be open for that day. The other number in here, this 1.3, oops, I'm having a time here, this 1.3 in front of the x, that's the thing that corresponds to the m in our y equals mx plus b form, and we know that represents slope. In terms of the application, the 1.30 stands for the cost per cup of coffee. So this is the cost to us as the business owner of producing and selling that cup of coffee. So we can interpret that as for every cup of coffee, it costs us $1.30. And so that means 1.3 is a rate of change. So it's dollars per cup, and it's a rate of change of the function. So we have the fixed cost and we have the rate of change of cost. And when the function is linear, the rate of change is a constant everywhere. So here's another example where we have the value of a car over time. So V of t is the output, which is supposed to be the dollar value of the car at time t. The input is t, where t is the age of the car. So in the equation, the 18,000 is the value when t equals 0. So if you put 0 in for t, you get 18,000. So this would be the value of a new car, because t equals 0. Remember, t is the age of the car. So a car that's 0 years old is a new car. The 2,000 is the rate of change. So it's the change in value for each year in age. So we interpret that 2,000 as $2,000 per year. So the units will be dollars per year. The units on the slope number will always be something per something. It'll always be a rate. So it'll be whatever the units of the outputs are, in this case dollars, per whatever units the inputs are, in this case years. So dollars per year because the outputs are dollars and the inputs are years. Notice that in the equation, the number in front here is really negative 2,000. The 2,000 is subtracted. And so it would be more appropriate, instead of saying the change in value for each year, we should say the decrease in value. So when the rate of change is negative, we think of that as a decreasing value. And then finally, when we have a function in a context, then we have to think about what the meaning of the variables are and everything so that we're not putting in crazy numbers. So for example, v of -5 would make no sense because there's no such thing as a -5-year-old car. So in this case, the t's need to be non-negative numbers. 0 is okay. 0 would be mean the car is new. And also, the equation can't possibly work if the t is beyond 9. And the reason for that is because v of 9 is 0. So you're basically saying that when the car is 9-year-old, it's worth nothing. So not only is that probably not exactly true, but it certainly means that v of 10 and v of 11 don't make any sense. There's no way that a car could have negative value. So, this is a good range, and you could fine tune it more than that. But definitely numbers outside of that range do not make sense for this equation. Okay. So what we want to talk about next is how we find these equations, like the one we have here, given observations about the data. So here are 3 different settings that we can have a function description. One is where we're describing just behavior of the graph without a reference to the function itself. The second one is where we're given function values, but we are told that it's a linear function, so we're told that the graph will be a line. And then finally, we have another setting where we're told that the growth is linear, and we're given some observations with the units. So we're given information about students and years. So let's look at these one at a time. In each case, we're trying to find either slope or rate of change, and the point we're trying to make here is that those really are the same thing. So slope between 2 points, this is something that you should know from Algebra 1. We're going to have the difference in the x-coordinates in the denominator. So we want the change in y over the change in x. The change in x, I'm going to always measure as the larger number minus the smaller number. So my x-coordinates are -2 and 4, and so I'm going to subtract those, but I'm going to subtract them in the order that gives me a positive answer. And then in the numerator, I'll have the y-coordinate that goes with 4 and the y-coordinate that goes with -2. So in the y-coordinates, I have the 3 and the 0, and the main thing is I have to combine them in the same order. So these two things go together. Those are the same point 4, 0, and these two guys go together to point -2, 3. So as long as the order is the same, then it doesn't matter which order you use. So this will be -3 on the top and 6 on the bottom, and that's -1/2. Notice that in number 2, when you're given an input-output pair of the function, so input 2 gives me output 3, input 4 gives me output 7, that is basically saying, well, it's exactly saying that the point 2, 3 is on the graph of G, and the point 4, 7 is on the graph of G. And so if we think of it in those terms, then we're going to do the same calculation we did before. The rate of change should be the slope calculation. So average rate of change is the same calculation as the slope, and I can do it the same way. The change in x's is 4 minus 2. The corresponding change in y's is 7 minus 3. And again, notice that I'm keeping the points together. The 4 and the 7 went together as a point. The 3 and 2 went together as a point, so I am keeping them in the correct order. And so that's 4 over 2, which is 2. And then finally, in the last problem, we could just make up a name for this function if we wanted to call it something. We could see P is the student population, and T would be the years. So the population in year T, and here population just means on Shippensburg's campus. So if that's our notation, then the problem is telling us that P of 2008 is 6,000. When in year 2008, there were 6,000 students, and in year 2014, there were 8,400 students. And so once again, I'm doing this average rate of change calculation, and it should be the change in the inputs on the bottom, and the change, oops, that's not the inputs. change in inputs on the bottom. So the inputs are 2014 and 2008. And again, I'm subtracting them to make sure that I get the bigger minus the smaller, and then the corresponding y values. Notice that the numerator here, so if you do this calculation, it's 400, but notice the numerator here, this is measured in students. In the denominator, these are measured in years, and so the units on this will be 400 students per year. So again, output unit per input unit. So if I'm doing the just regular rise over run calculation in terms of a graph, or if I'm doing the average rate of change calculation, it's all the same thing. So if we want to find the equations of these three things, these lines, you probably have some way of doing that, and you were reviewing that in Review Module B. But let me just tell you what I do. I always use what we call point-slope form. And one reason is that this is the form of a line that you see most often in a calculus course, because in calculus, it's not unusual at all that the information about a line that you have is a single point and the slope of the line going through the point. It's less common in calculus class to have 2 points given to you, and that is what you're most used to in an algebra class. So this is point-slope form. So let's look and see how we do that. We'll look at the same functions because we've already calculated the slope. So in this one, remember the slope here was -1/2 from a couple of slides ago. The slope here was 2, and the slope here was 400. So whether we call it rate of change or average rate of change or slope, it was all the same calculation. So according to the point-slope formula, my function is going to be my slope times x minus something plus something. And the somethings here are going to be an x-coordinate and a y-coordinate. And I can use either one, and so it makes sense to use, if one of them has no negatives in it, that's a plus, so to speak. And if one of them has 0 in it, that's even better. So I'm going to use the second point because I can choose. That point 40 has an x-coordinate and a y-coordinate. And so I'm going to put the x-coordinate right here, and I'm going to put the y-coordinate right there, and that's the equation of my line. If you want to simplify that, meaning do the distributive property and simplify the right-hand side, that's great. That'll turn out to be slope-intercept form if you do that. But unless someone asks for slope-intercept form, there's no reason to do that extra step. All right, so we'll do another one. In fact, you might want to do the other two and then just see what the answers are. I'll pause and write the answers in while you do that. Okay, so here's what I got. You can see in each case which point I've used, because I'm using data from only one point in each case. So you might ask yourself, what happens if instead of using the point I used, you use the other point? So what would happen if you did use this other value? What would happen if you use this other point? What would happen if you use this other data? I invite you to try it. It may not look exactly the same when you write it down, but if you are to simplify the right-hand side, as I said, that would give you the slope-intercept form. You'll see that even if you use the other value, you should get exactly the same thing. So you should end up with the same formula regardless of which point you use, but you may have to simplify the right-hand side to see that.